All right, so in this particular video, we're going to talk about the second basic cache replacement policies, Belady's optimal. And this Belady's optimal is essentially some offline cache replacement policies. Okay, so many years ago, Belady has demonstrated that there exists a simple policy which he called OPT, or mean optimal, or minimizing, something like that, which always leads to the fewest or the most optimal number of cache misses, or the most number of cache hits. So the core idea behind this offline policy is pretty straightforward. You just try to evict the page that would be accessed further in the future. Okay. So here, let's first define the term offline. So Belady's optimal is essentially an offline policy. So offline means we are base this policy on a very important assumption, which is assuming we know about the future, we know we have perfect future knowledge, which also means you could think of this offline as something like, given that we know about the whole memory access workload traces, and we know exactly at what time which memory page, which physical memory is going to be referenced. Okay, so this is the precondition of the so-called offline algorithm, and this is dramatic. This is completely different from the previous few cache replacement policies that we've learned, which are FIFO and random. These are all online policies. Because online, we don't know about the future. We don't have perfect future knowledge. This is also practical algorithms, where this offline Belady's offline optimal algorithm is not practical, okay? Because it's impossible to implement in practice. Because it's simply because we don't know about the future, okay? And the intuition behind the high-level idea of Belady's optimal offline algorithm is we try to evict the most useless, the least useful item within the cache. So how to quantify, how to define this usefulness is by looking in the future and see when exactly it appear in the near future, in the future. And we check the timestamp when it gets re-referenced, gets reused. And if the distance is the longer distance is, the less useful it tends to be. Okay, we try to basically evict the item that is referenced the most distant away from the now. Okay, but this is greatly useful because we could effectively use Belady's optimal as a practical best case baseline, for comparison purposes. We could compare the performance achieved under offline algorithm against a certain online algorithm. And the wider the gap is, the less performance this online algorithm tends to achieve, right? So here, this slide, I include a paper which shows a short proof of the optimality for Belady's optimal or Belady's mean algorithm. Okay, so for those who are interested, feel free to take a look. So let's next take a look at how Belady's optimal works. Okay, here again, we reuse the same old example, extremely simple example, right? And again, let's use this 4-column cache simulation table. And the leftmost column shows the access pattern, the reference workload, okay? So assume the cache size is 3, which means the very first 3 memory accesses are always compulsory misses. Okay? And then the next 2, 0 and 1, because 0 and 1 has already been cached within the memory, so there will be 2 hits, right? Okay, so the next 2 references are all cache hits. And next is reference to physical frame number 3, right? So over here, you examine the content within the cache. 0, 1, 2, so there's no 3, meaning there would be a cache miss. So then you have to make the decision with regards to which one out of the 3 you have to evict out of the cache. And here we refer to how exactly Belady's optimal works. We look into the future and we see the next reference is 0. So meaning 0 is safe because 0 has just been referenced in the very near future. And then we see 3. 3 is out of the cache, so we don't consider that. And then we move on to 1. And 1 is over here. 1 is also safe, right? And then followed by 2. 2 is over here. But the reference to 2 tends to be the most distant future reference, right? Away from now's timestamp, away from the time to get access to the next reference, which is 3, okay? So this is the distance reference. So which tends to evict 2 over here. So we evict 2 and instead insert 3 over here. Okay, so this is how exactly it works. So what to evict? We identify page 2 happens to be the one that will be accessed further in the future, the most distant access. So we evict it as a victim and then replace it with 3. Okay, and next, hit, and hit. All these 3 are hits, obviously. And then when it comes to the next reference, which is 2, you just scan through the whole content within the cache. 0, 1, 3, there's no 2. So then again, you have to make the decision with regard to which one you want to evict. Okay, so this example is a little bit trickier than the previous one because the next reference, so there's only one next reference, which is 1. So that at least means that 1 is safe, but you still have to make decision with about out of these 2, 0 and 3, which one you want to evict. Okay, so here we could assume if there's no future reference, if there's no future access for reference, you want to break the tie by applying some random policy where you could either evict out 0 or 3, and the chances for evicting either of these 2 is 50% in this particular case. Or the direct way, the straightforward way to break the tie is, let's assume you have the future access over here, which is 3. Okay, so which means 1 is not the end of the trace. In this case, 3 is also safe, and the only one left is 0. So 0 tends to be the victim. But here, as you can see, it kind of depends on the situation. Okay, so if you are given a question where 1 tend to be the end of the trace, pretty much you need to use this random policy to break the tie. Okay, so let's see what happens over here. So what to evict? So 1 will be accessed after page 2, so 1 is safe, right? In this case, we evict 3, and assuming this is some result generated by the previous random generation, okay? And then we replace 3 with 2, and the next one is another hit, okay? So in this case, let's take a look at the performance of this whole workload by counting the total number of misses or counting the total number of hits. It's exactly the same. So the total number of misses in this case is 6. That means the optimum performance, the best performance this a possible online cache replacement policy could ever achieve is the same as this 6 cache misses. Okay, so the best that you can achieve is 6 misses for whatever cache replacement policy is given exactly the same workload, given this workload. Okay, because Belady's optimal is proved to achieve the best performance.